Okay, so the concept here with Zeno's paradox is we keep adding something that gets infinitely small, and those infinitely small chunks effectively don't amount to anything significant. So the concept is you will learn situations being added up to infinite number of values. Consider the result adding infinitely values the exact sum or only an approximation of the true sum. That's the question. It's really probably an approximation.
Very close
Calculus,
terms.
the idea with calculus is always taking everything to infinity. Or getting infinitely close. When you'll do areas and you'll put an infinite number of boxes in a finite space. And the techniques of calculus get you there.
Use E, right?
That's why E is used a lot and works really well. TOK connection. When you began investigating the sum of infinite series, you may have asked yourself, how can an infinite series have a sum? Good question. This gets into language in a way of knowing that requires us to expand our knowledge of the concept of sum infinite series headed towards an endpoint, and they are either convergent or divergent. Convergent meaning your ratio's getting small, has to be between 1 and -1. And divergent means no, there will not be an infinite sum. Mhm. So here is the general sum formula for a geometric series. If, or in this order, I think this is the order I have in the packet. This is the order that IB has in their packet. Reverse the order, you just add an extra negative sign to top and bottom, which cancels out. If R is less than 1, 1 minus R to the infinity, R is less than 1, becomes 1. So this formula for for convergent infinite geometric sequence just becomes that. First term divided by 1 minus the ratio. Very, very simple formula. So we've done some of these. You've kind of have the idea from pre-calc of, yes, I can keep adding these up. And this one looks like the ratio is 1/3, so the sum would be 1 over 1 minus 1/3, 1 over 2/3, which is 1 over 1 times 3 over 2, or 3 over 2 over 1.5.
It's a ratio.
Well, that's the sum. So if I add all of these up forever, I will be getting closer and closer to 1.5. It's a really easy formula. Yes, the ratio is, I'm multiplying each one by 1/3, so that's R. This only works between 1 and -1 because those are ones that are getting smaller and smaller and smaller. It doesn't work. Here is this thing in summation notation. Same sequence. Starts at 1, goes to infinity. 1 times 1/3 to the I minus 1.
Wait, what? So the
Original formula? So the original formula looked like this here. If R is
less than 1.
if R is less than 1, r to the infinity goes to 0. Or I should say, this would be using better notation. No, not as r goes to the infinity. As n goes to infinity of r to the n. It just goes to 0, so that becomes effectively 1. I think I like it being in the way of 1 minus r to the n, because then you get 1 minus 0.
Mhm.
And so that's the formula you get. As long as absolute value of r is less than 1. Has to be less than, not equal to. If it is not, it is divergent. There is no infinite sum. So, looking at this dot 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 here at the end indicates that it's going to keep going forever. So I'm going to evaluate this sum. What is my common ratio? Negative 1/5.
My bad.
Okay, so 4 over 1 minus negative 1/5. That's 6/5. So multiply by my reciprocal. 20 over 6. 10/3 is my sum.
Okay. Makes sense.
Is this series convergent or divergent?
I think it's divergent because it's equal.
It's equal to 1, yes.
Negative one.
The ratio's negative 1.
Once.
Yeah, this is gonna alternate between 1 and 0. It's not diverging to infinity, like anything greater than 1, but it is,
Because it's negative.
yeah, because you look at this term, that's 0. Third term is 1. Fourth term is 0, or fourth sum. It would diverge to infinity, but this negative 1 alternates. And that's what's often called an alternating series. You do a lot of series thing, or a decent amount in calculus 2. They're kind of hard. Yeah, you said that. I don't think you'll find them as hard.
Scraps.
Well, yeah, and the IB questions about them will give you weird things in the middle and ask you to write a lot of equations. Where the trick to kind of every high level math class anywhere, whether it's calculus 2 that Izzy's in or
Growth test, I was like one step away.
yeah. The trick is writing down what you know, what you don't know, getting it into equations, and then figuring out how to put equations together. A lot of these arithmetic and geometric sequence ones are you'll need 3 equations that you'll have to combine together through a combination of substitution, mostly substitution. Okay, for a geometric sequence, the sum of the first 3 terms is 91 over 9, and the infinite sum is 21 over 2. Find the common ratio. So 91 over 9 equals U1 plus U2 plus U3. All of a sudden, the difficulty picked up from something that was really easy. And the infinite sum is 21 over 2. U1 over 1 minus R.
And what are we trying?
We're trying to find R and U1 actually. So I can rewrite this one because U2 is U1.
Plus U1 times R
Yep.
plus U1 times R squared.
Yes.
Perfect. And I'm okay.
So I'm going to take this one.
Yeah, I don't know what to do there. Ooh, factor.
I'm just multiplying it, so I'm solving for U1. And now I'm going to plug that into the other one
For U1, like
for all the U.
Yeah.
I'm going to factor out a U1 there too. So effectively, I've factored out this U1.
Sense today.
It helps when you can talk through it. And then I'm going to go to the calculator and solve by graphing. So I took this, where I factored it out and substituted in for that U1 instead of having to substitute in 3 times. And we're going to solve this by graphing because I don't have any desire to solve that by hand. Oh, I missed the minus 91 over 9. There it is. So hopefully you're comfortable solving by graphing now.
Like definitely on the 84.
Yeah, make sure I don't have my
Forcing myself to use this.
good plan because it's going to be a lot nicer uh next week when we get to matrices
Oh, the matrices are like I feel like I've gone and given that.
on on this one.
Yeah. Okay. So just everything.
Yep. Make sure you use an X for the R.
Only ever use X's.
Yes. When graphing, only use X's. Or equals 1/3.
Wait, okay. I need to go to menu and then edit my window.
I did just zoom standard.
We're just finding the Excel site.
Yep.
Oh. Oh.
Make sure I'm right. Yep. normally I'll probably open the calculator software app, but yes.
Okay.
And then to get U1, I just plugged in,
One.
I took that equation because it was already solved for U1. Seemed a lot easier than anything up here.
No, that actually made sense. The thing I wouldn't have done was factoring out the U1, and that probably would have made things worse.
Yeah, it definitely made things better to do it.
Actually, I don't know if I would have multiplied the. I don't know if I would have even gotten this far.
Not that bad once you've seen a few of them. You'll have to get used to it.
No, it makes sense. I just don't think to do these.
Yeah, that's what you. That's why you're not ready for the exams, and a few other parts. But
I feel like there's just like a lot of math I haven't learned yet. So
yes, but you're not ready for the exams on this. Okay, can we keep it down, please? So, write an expression for r times s infinity in terms of u1 and r. So we're told this, correct?
yeah.
What is the sum to infinity? Or r times s infinity would just be r.
What are we trying to write an expression for r times sum of infinity here's a symbol. I don't really understand what they're asking.
Well, they're asking me to multiply r times s infinity, so I'm just multiplying it in. In terms of u1 and r. I'm not sure quite what they're asking either.
So I was just gonna move everything one term up.
Yeah,
It seems. Like I feel like they didn't accomplish anything. No, well, first,
So
that's right. Why
s infinity, yeah, that's part A. So then all terms of the right-hand side of s infinity minus r. Oh, okay. So here we've got s infinity. This is a little trick. S infinity minus r times s infinity is basically moved everything up a term, correct? So when I subtract them, I'm left with just u1. Does that make sense? This is a little proof trick.
we
So I took
subtracted
s infinity, which is this,
r times
minus
okay.
this, and this term is the first one there.
So this is like a way you can find the first term if you
Mhm.
don't know it.
Well, not really.
No, because you need the first term for
So you need the first term. So this is a proof for the formula, is what it's doing. So they did s infinity minus r times s infinity, which they should have given you a hint on that. And the sequence is, yes, technically, but because this goes forever, technically this is the third, that's going to be the fourth canceling out, but they go forever, so it just doesn't matter. So when I subtract this, I've yes, shifted it down one, and that equals u1. If I factor out an s sub infinity, I get that. The factor in S of infinity from these two. Then if I divide, I kind of gave you a loose justification before. This is a formal proof justification. And I'm going, oh yeah, I remember this from when I took analysis a couple of years ago. And we had to do those proofs. The little trick of essentially multiply it and watch the terms.
So explanation, but this is good too.
So that's what formal proof looks like. If you mid, no. The understanding proofs will help you solve problems, but you will not have to do a single proof. They will once in a while say show,
Show.
and that just means usually show means plug it in and work it out. They're telling you, they're saying, work this thing out, but then they tell you what it's supposed to be at the end. That's something you might have to do.
Down at the bottom, at least.
Yeah, that type of thing. There are no open-ended proofs. And you do depending on your major, you do a few proofs, unless you major in math where you do a lot of proofs.
I think I'll do some type of engineering, so I'll be doing some proofs, but
Just a little bit, actually. The engineers don't do very many proofs, they solve the problems. The math people prove things and don't solve nearly as many problems.
do RPC though. Even do like computers, maybe PA or something.
Yeah.
I don't really know yet. Probably like
See.
healthcare engineering, just really branching out from the family here.
Healthcare engineering. Yeah.
You say.
It's okay.
Good career stuff.
Yes, both very good. Okay, so applications of this. So we've got all these squares drawn in here, right? The shaded areas are 1/4. Diagram 2, it's 5/16 now. So I got a fourth plus a 16th. This is plus a 64th.
The ratio is 1/4.
The ratio is 1/4. Same idea. So draw a square with the unit divided into 2 equal parts and shade one of them. Then take the unshaded part divided into 2 equal parts, shade one of them. So we're doing half, right? Calculate the total area of your drawing that is shaded. Continue until you had 6 shaded areas. Okay, so we've got 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus 1/64. And if we add these up, that's 32. I think we're going to get 63/64.
Wait, why? Did we start with 1/2? Then was one.
Because it told me to divide it in half for this one.
Oh, okay. I thought this was
Slightly different problem than the pictures. So let's double check my addition. I can type it in right. Yes, it is 63/64. If you continue this indefinitely, find the total shaded area. Well, it's going to always be one whatever less than, if it's a finite amount, it's 1 minus 1 over 2 to the number of terms. That makes sense. If it's not a finite amount, if it's infinite, it's just going to converge to 1. What does it mean? Eventually, you're practically shading the entire thing.
Like a finite amount of terms is what you meant, right?
If I had a finite amount of terms, as opposed to an infinite amount. Now, right, this is a rational number. I can tell you that that's 7/9. But here's the, how are they doing it here? So, okay, they're doing it as a series. So that's 7/10, that's 7/100, that's 7/1000. So we have a series with U1 equals 7/10 and R equals 1/10. So if I stick that into my formula, 7/10 over 9/10, and I get 7/9.
Start a formula.
What is 0.9 repeating equal to?
1.
It is 1. It's 9/9, right? Which is 1. So you can use these to show bouncing ball patterns.
Oh, because it goes.
So ball is dropped from a height of 3 meters. On each bounce, it rebounds 70% of the previous height. Calculate the total distance covered by the ball on its way up after the first 3 times it hits the ground. So the trick to this is it's not 3 meters isn't the first bounce.
Also, I feel like this only works in like a perfect world where like there's no energy.
Energy loss, yeah, it does. Most physics is done in a perfect world. Yes. Yes, most physics is done in a perfect world. Uh, Big Bang Theory, yeah. That's not young Sheldon, it's the old version. So it's just not on the big apps I have.
Yeah, we have like the. I think we
So
have
I
the
have,
this. My dad really likes it.
yeah, your dad talked about it a lot.
And Jones.
So calculate on the first 3 bounces. So this is U1. So essentially I'm doing the first 3. So S sub 3 is 2.1, 1 minus 0.7 to the third. I don't think there was an n minus 1 on that. 1 minus 0.7.
What's my first term by 0.7 to get the second term?
No, because it says on the height way up. So the first 3 bounces. It was dropped from 3 meters, comes down, bounces up to 2.1. So that's the first height
Oh,
because it says only on the way up.
That makes sense. So 2.1 is really a sub 1,
A sub, yeah, or U sub 1.
u sub 1.
Yeah, they're using a lot of U's. I always used A before this. So 4.6. If we carry it out,
Use an A on base.
no, I don't think so.
I'll use a U, but like
You're get used to it, yeah. Eventually I will too. I taught it with A for so many years. If I do infinity, it's 7. If, do you know how you do total distance covered? Kind of wish they actually asked that question.
would it just be? I thought that would be the infinite sum.
No, this is the infinite sum of the distance covered on the way up on its,
up though.
yep.
So would you add you have to add 3 meters.
So I need to add 3 and double this, right?
Yeah.
So 2 times 7 plus the initial 3 should be 17.
Oh, okay.
And theoretically, just like Zeno's paradox, the ball never stops bouncing.
Because after the first three, everything is gonna be double,
Yeah.
because it'll fall back down.
After the first drop, it's going to fall the same distance it went up.
Yes, this makes sense.
I'm shocked they didn't put that in the example, but it's probably in a problem somewhere.
Total distance.
Yeah.
This you gotta figure that out.
You have to use your brain, and that's a very IB way of thinking.
That's why we didn't.
Yeah. As like IB will challenge you to,
Questions are good because that's like how you use it in like an actual.
yeah. They challenge you to be ready for a job. Yeah. Like, okay, solve this actual problem. Yeah, sorry, the problems aren't unrealistic about watermelons in the back of a truck anymore. How many watermelons could Steve put in his pocket? And you're like, this is ridiculous. Who does this? Nobody. Be thankful, those were easier. The more realistic it gets, the harder it gets. Okay, that's it for today.